So good morning, everyone. Good afternoon. Or this is Giacomo speaking, and I guess we are already online. Let me check just to be sure that everything works. Yes, I think so. So it's a pleasure to host this new event. I just started straight because today, unfortunately, and with big surprise in a sense, it's the last event of the Hypatia Colloquium series. The time passed very quick this year, and as last year we had a very, very beautiful and long series of talks by early career scientists. With this event now, I would like to just once again, first of all, congratulate with all the speakers of the entire series, of the speaker of today, plus the speaker that we had during this winter time, to congratulate with all the speakers because of the great science that you are doing these days, and of course, especially because of the still not optimal condition in which the astronomers, in which we are, and not only the astronomers, but in which we are working. So it's a pleasure for us at ESO to be able to host such an event, to give this platform to you and to the early career scientists. And we hope that this is soon going to be, times are going to change and we can go back to fully to what the reality was before pandemic. And then events like this one will not be as necessary because you will be able to again enjoy, the scientific environment and the scientific life through, in-person contact with your colleagues, with our colleagues, and with the community. We will next year. So first of all, the other thing I wanted to say that we are collecting the proceedings for the contribution from the speakers. So I encourage, first of all, the speakers. We didn't collect yet all the contributions. So we will soon. Hopefully I get all of them. So, but the booklet looks already very beautiful, and it's going to be very similar to the one last year. Just to show you, this is the beautiful booklet with all the. You can find the version online anyway on Zenodo, and on our pages you can download the PDF. And of course, we will collect the one of this year, and then we put it online as soon as possible. The other thing is that, again, if you go to our web pages, you will see the program of this year. You can still see a link to all the talks that are available on YouTube, and there is a dedicated space, a dedicated playlist for this year and for last year, where you can see all the talks, and also you can download if you go to the program, you can click on the links there on the titles, and you can see the picture of our speakers, you can see the title, the abstract, and also you can have a look at the CVs of the speakers. And please go there and have a look at all the participants of this series. For next year, we haven't. Let's see how we will continue the series. Whether we will find a new format. Let's see. We don't know yet, but we will try to find a solution to still serve our early career scientists and support our community, which is what really we want to achieve with this series. And with that, I think I can start introducing the speaker today. I will have the pleasure to chair the session, and the first speaker of today is Carolina Cenzano. So let me see, because I lost. Yes. So Carolina, she got the PhD. She's from Santiago. She got the PhD, the bachelor studies at the PUC, at the Pontificia Universidad de Chile, Católica de Chile, and now she's doing the PhD there, and she's working in detect and characterize overdensity in streams. And today, in fact, she is gonna tell us about exploring overdensity in the Milky Way halo using machine learning and RR Lyrae stars. It's in fact a topic that is really exploding in terms of potentiality, both technical and scientific, during the last month and last years. So I'm really looking forward to hear about that. So Carolina, please, you can start sharing your screen. Yeah, very good.
Can you hear me?
Yes. All looks fine. You can go in presentation. Yes. Excellent. Excellent.
Thanks for the introduction. And yes, today I will be talking about my current topic of work, that basically is to study RR Lyrae stars that are from different overdensity candidates, and I analyze them using different machine learning techniques, especially cluster algorithms, in order to analyze their kinematics, or whether or not these overdensity candidates can be in fact overdensities. And so every time in this talk I'm talking about an overdensity, I am referring to these remnants, like the stars that are stripped from merged events that occur for our galaxy many years ago, that gave the current form and structure of the Milky Way halo we know nowadays. And I'll talk here about stellar streams, clouds, and shells, because no all overdensities have the same shape. Their shape, for example, here is Hercules Aquila cloud, that the stars are like widespread. And then there are other things like streams, where stars are more nearby each other. And what will determine how is the shape of this overdensity will be a series of factors: how long ago this merging event took place, how were the conditions, it was a global cluster or a dwarf galaxy that was accreted to the Milky Way. So yeah, there are very kinds of serious types of different overdensities, and these ones that are like very narrow are usually called cold streams, where the particularity is that all the stars that conform them have very similar radial velocities to each other, while in clouds they don't really. And well, you can see, as it was mentioned, this is a very in revision field of investigation, because you can see the difference between how many overdensities were discovered until 2019 and until today. It has exploded the numbers, and I think that here is not even all of them. So yes, it's a current very interesting and is changing a lot every day, this field. So a little summary of what RR Lyrae stars are. Well, they are pulsating variables that you can find here in the instability strip. Well, they are old stars, and they are basically, most of them are metal poor type of stars, but really they are mainly known because as distance indicator, because they are standard candles, because there is a relationship between their period and their luminosity, meaning that with knowing the period of these pulsating variables, you can obtain like an absolute magnitude, and with that we know that you can obtain distance from that. So here is like a typical light curve for RR Lyrae. And during this talk, whenever I'm talking about RR Lyrae, I'm talking about this specific type, because there are different types of RR Lyrae, and it's called RRV, that are the RR Lyrae that are pulsating in their fundamental mode. And really, this is because this is the most typical type, and they have a very unique light curve. So they are not usually confused to other type of variables, unlike the other types. So, well, how can we relate like pulsation variables with stellar streams or overdensities? Well, the thing is that RR Lyrae are very good to find new overdensities. Of course, there are many other stars of different methods that other overdensities can be found, but some of them have been traced using RR Lyrae, really because, as I mentioned, RR Lyrae are standard candles, so you can know their 3D position in the celestial sphere. So when they are like, since they are like in the instability strip, they are rare in comparison to the main sequence, for example, but they are not rare enough, so you are not expected to never find them. So I love this phrase from Stringer et al. In 2019 that explains that they are a rare type of stars, but not enough rare. So it's not common to find two RR Lyrae or more nearby in 3D spatial position and not being them related to the same structure. For example, globular clusters, or in this case, an overdensity. So in this plot that is from Torrealba et al. In 2015, what they did was to have the 3D spatial position of a series of RR Lyrae from Catalina survey, and they compare the density of this survey when they compare with the underlying distribution, like expected distribution in the stellar, in the Milky Way halo. And by comparing it, they can found that in a series of places, there were more RR Lyrae than expected. So there were overdensities of RR Lyrae. And with that, they were able to find 27 overdensity candidates. And for example, as a matter of fact, they also found known things with this method, just comparison of the expected RR Lyrae distribution with the one that you can see in stellar surveys. And well, but one of the limitations of this method is that since it's using RR Lyrae, you can only find all the structures and metal poor structures. So for example, this one, if my memory is not tricking me, these ones are globular clusters, and this is the Sagittarius stream that is a very common one. So my motivation really here was to study different machine learning techniques, because we are bombarded with new and new surveys, like a very big amount of astronomical data every day. And also because, as I told you, there are many types of overdensities, but most of the ones that are like for many, for big data, are only focused to cold streams. So I wanted to see if there could be a possibility to study in a more efficient way these overdensities, but without this limitation of only cold streams, for example. And well, my biggest motivation was that we have a sample of RR Lyrae that is very unique. Our sample of RR Lyrae came from actually 11 of the overdensity candidates found in Torrealba et al. 2015. And what is unique about them is that we measure the radial velocities and metallicities by taking the spectra of these RR Lyrae. And why is this so important? What is so unique about our sample is that in most of the surveys of radial velocities, for example, there are not many variable stars there, because taking the spectra, a good spectra of variables, is really tricky, it's really complicated, because you have to know the light curve very well, because since they are changing their magnitude all the time, you have to know exactly when the light curve is changing, in which phase the light curve is changing the less amount of magnitude over time. So many algorithms many of these huge databases are more used for not variable stars for this reason. So it's really rare to have RR Lyraes with meditions of the radial velocities, and this is why our sample is so unique. And well, I had to include this because, as you all know, Gaia Year 3 just came out last week. So maybe you're thinking, oh, but now in Gaia there are a lot of radial velocities, and it's true, there are 50 millions of radial velocities, but in the case of RR Lyraes, the sample contains like approximately 400,000 RR Lyraes, but from that, less than the 5%, well, less than the 3% of them have meditions of radial velocities. And actually, our sample of RR Lyraes didn't even, most of them didn't even make the cut of brightness for this radial velocity survey in Gaia. So it's still not that common to have radial velocities, and also for these things that I'm talking about, how these algorithms usually work, it's about now we have to start analyzing how relatable these radial velocities in Gaia are because of these complications. So here is the spatial distribution of some of our overdensity candidates. For example, here we have CEN3. It's one of the most, the ones that we have more attention of, because we can see here that is going through, it's really like on top of some known structures like the orphan stream. The same happens with Corvus 01. And here is a sum of this part. Because what makes us very interested about, for example, CEN03 was that it's crossing orphan overdensity, but their distances are very close by to other stellar streams that are nearby, but they are not like really these seem to be really nearby, but if you zoom in up, then it's like not close enough. So this is very interesting. Maybe they are related, or maybe these overdensity candidates are related to orphans. So there are a lot of science that can be done of them. And well, here is even more a zoom of at what I'm talking about. Like you can see that it's nearby, but not nearby enough. And yeah, we have other overdensity candidates that also happens to cross or be really nearby known structures. So our data sample is very interesting in that fact as well. So what I did was to study at first different machine learning techniques, especially clustering. And finally, after exploring most of them, we found out that DB-scan could be really useful to detect overdensities, like different types of overdensities, because it's an unsupervised learning machine technique. So this means that whenever you put the input data, will not have this scientific bias because it does not require to know the exact number of clusters that you are like putting into the algorithm. And also it can detect noise points data, so it can detect if the RR Lyrae of our overdensity candidates are in fact from their overdensity candidates or not, because the noise points will be these stars that we are believed to be part of the cluster, but actually not. It detects unusual shapes, like for example here, coming since another common algorithm cluster, but it cannot, it is more like distance spaces, but this can find like unusual shapes based of density and not just distance. And well, these algorithms have been used in astronomy for a long time now, but basically more in 2D, not as much is like taking more amount of considerations. So the two important parameters of DB count are minimum samples and epsilon value, that basically epsilon can determine how close the stars must be to one another to be part of a cluster. And the method that we are using to determine this value is called, well, sometimes it's called the elbow and sometimes the knee curve. And it's because this is an algorithm to determine the best value of this distance, that this distance is like an Euclidean distance between all the parameters. In our case, they are 60 parameters because we will be using the 3D position of our Lyrae stars, proper motions, and radial velocity. And the optimal values of epsilon will always be, can be found from this type of graphs, of plots, because here, like in the knee or elbow point, you can find an optimal value where there is not too much chance of being overfitting, for example, the clusters. So how at first we wanted to know if DB scan is actually worth of trying by using it in known overdensities. For example, a very important one is Virgo overdensity. And why we decided to use it? Because it's one of the few ones that have been studied with RR Lyrae, and they have their radial velocities measured it too. So in 2016, Vivas et al. Found a sample of 412 RR Lyrae stars, and then made 10 different subgroups of RR Lyrae inside this. And if we try to compare these subgroups, that these subgroups are basically done by the difference between the RR Lyrae inside the Virgo overdensity, difference related to radial velocity and distance between one another. And if we analyze this overdensity using this scan, we can actually find very similar structures as they were found in 2016. And using our measurements of using the same measurements of radial velocities they have, and we have a very big completion, especially in the sense of the structures, the groups characterized by them that are very small. but sometimes, but it's not like these groups are not set in stone. So sometimes the clustering found a completion, but like mixing different types. But the thing is that it recognized that there are patterns between the stars. There are like different groups inside this group too. So with that, we can like measure the efficiency, and in terms of completion, we had like the 90% of completion. So if it works for known overdensities, well, it can be used for overdensity candidates too. So we did that with our samples, and these ones are the samples recovered by Torrealba et al. In 2015. And this is the distribution they found out just using the 3D data. But if we incorporate the proper motions and the radial velocities, then we found out that even if some of the clusters that they say that they were candidates are really nearby one each other, the radial velocities between them are in fact enough different. So for example, here when 101 is, it was believed to be one big overdensity candidate. This can suggest that maybe they are two different because it has their kinematics are different. Also, we're currently doing an orbital analysis in these overdensity candidates. And because in the literature, orbital analysis for overdensity candidates are really important to determine if they are actually have the nature of known overdensities and its possible origin of these overdensities. So, for example, Hercules Aquila, here in the map, was discovered in 2007, but in 2014, a sample of RR Lyrae with radial velocities was proposed, and in 2019, with Gaia DR2, like meaning with the proper motions too, orbital analysis was able to be made. For example, here is a recreation of this orbital analysis, including two of our overdensity candidates. Here is a sum of the important things I want to show you. And the thing is that what it was concluded in this paper is that here Hercules Aquila has a large eccentricity in the orbital parameters. And we found out that, well, for example, two of our overdensity candidates have a similar distribution to them in terms of radial velocity, of angular momentum, and eccentricity, like going from 0 to 1 as well. They found out that both Hercules Aquila and Boyd have this similar like distribution too, and in the paper they suggest that this evidence means that they are both from the same origin of this overdensity, that they suggest could be Gaia-Sachias, among other evidence, of course. But the thing is that here we have two of our overdensities having very similar orbital parameters as two known overdensities. So this can suggest, of course, we need more analysis, but this can suggest that probably if they found out that because of their eccentricities and their orbital parameters are similar, they could be from the Gaia-Sachias. This means that our overdensity candidates are in fact having the distribution of similar to known overdensities, and they similar to the ones that are probably from the Gaia-Sachias. just from a comparison of what I'm talking about, for example, our over-density candidates are not slightly like similar to cold streams because, as I mentioned, their radial velocities tend to be more less wide. So yes, our current evidence is that they have similarities. Our overdensity candidates have similarities to known overdensities in the literature, but as wide overdensities and not cold streams, for example. So we have, nowadays we also have limitations because DB-scan is not very good with measurements with errors. For example, there are measurement errors in our sample of radial velocities. And also we have this incredible like bias of how to find the perfect epsilon value, but we are currently making an algorithm to take in considerations all these errors. And yeah, well, it's our conclusions that DB-scan has been able to found quite difference and was able to interpret the data quite well, and that our data also has orbital parameters similar to known overdensities in the literature, and that, well, in the future, we have to increase these to put in consideration these measurement errors, and we have to explore more the radial velocities of the RR Lyrae in Gaia DR3 because we still have, it just came out, so we have to see how relatable they are in order to do this analysis on them again. So thank you very much for listening.
Very good. Thank you very much, Carolina, for the talk. And thank you. I will check the chat on YouTube and the chat. I will, if anyone from Zoom would like to make a question, I remind that just please raise your hand using the raise hand button in the Zoom panel, or if online, you can just write the question on the chat, and then I will pass it to the speaker. While I wait for people to make their question or raise your hand, I would like to make a question actually. So, Carolina, indeed, you showed us the importance of radial velocities to distinguish, like the case that you show us, to distinguish that you can really, what in 2D, let's say, projection was thought to be a cluster, then if you look at the third dimension, then you see that this is not the case, like you showed us. But I was wondering, so now it's interesting now that you mentioned that you now we have this data DR3, Gaia DR3 data available, but in fact, you as a future perspective, you expect to verify those data and understand how the radial velocity. So I was wondering, what's the strategy there in your opinion? So how to do this? Because it's going to be a massive work, I guess. Critical, yes. Very important, actually.
Yes. Well, the reason why I have to first conclude if they are relatable, it's because of many conversations I've been having with people working in Gaia that probably the algorithm is not, in fact, variable stars friendly for radial velocities, as you can say. But our strategy will be to find if these are Lyrae spheres where you can find our Lyrae with radial velocity in Gaia, and started like by sections, doing the DB-scan analysis by sections of the Milky Way and not just in all the space. Because in that matter, we can determine if they are in fact from known objects, and and don't waste time by trying to reconstruct things that if we put in all the celestial sphere, maybe they are not likely to be related in that case.
But do you have so you were mentioning this, but so you said that your sample of RR Lyrae for which you have spectra goes below the limit of 14, right? But do you have still some stars in common with Gaia that you can use just to...
Yeah, but they are like, in our sample, they are like 7, something like that.
Okay. Well,
yeah,
not bad.
Yeah, but that is thing because some of them they are not quite, and they don't have like the same radial velocities, and that's why I was mentioned that maybe it's not because of our data it's wrong, or maybe it's because data of Gaia it's better, but maybe it's because of this thing that it was taken in another path of the light curve too.
I see.
If we have to analyze where it was taken these radial velocities first,
with respect to
which path of its light curve is very important.
Yes, very good. Thank you very much. Let me check if there are questions. Someone from the speakers, sorry, from the attendees, if someone has a question. So no, then, well, okay, thank you, Carolina. Thank you very much. Congratulations again. And we can now move to the second talk. The talk from Feliciana. Feliciana, you can welcome. First of all, you can start.
Good afternoon.
So Feliciana is comes from works at the University of La Sapienza di Roma, in Rome, Italy, together with INAF and the Istituto, National Institute of Astrophysics, and she is doing the PhD there. And today she's gonna talk to us about the very back to the fundamental physics, which is something that we not very often heard about. So this is really thank you very much for that. And in particular, this basically testing general relativity with the Galileo satellites DORESA and MILENA, which are two of the constellation of Galileo. So excellent. So thank you very much. Looking forward to hear about this. So please, whenever you're ready, you can start sharing your screen and start with your presentation.
Okay. You can see the screen, the slides?
Yes, very well.
Okay. So, good afternoon at all. I'm Feliciana Sapio. Thanks for giving me this opportunity to speak about my project in this exciting scientific context. I will present the Galileo for Science project in which I'm involved as a PhD student at the Istituto di Astrofisica e Planetologia Spaziali in Rome. This project is funded by the Italian Space Agency with the collaboration of the National Institute for Astrophysics and Torino Politecnico. I will start with the description of the Galileo Fox satellites of our interest, which are those on eccentric orbits, and with the main goals of the project. Then I will give a brief overview of the linearized theory of general relativity in the weak field limit, which is the mathematical context on which this project is set up. Then I will focus on the precise orbit determination and on non-gravitational perturbations models, showing some preliminary results of our analysis. After, I will explain the implication in cosmology and in fundamental physics that the measurements of this project can lead. Finally, I will give the conclusions. In August 2014, two satellites called DORESA and MILENA of the European Global Navigation System Galileo were launched. They were erroneously placed on elliptical orbits, so useless for navigation. However, this incident offered a rare opportunity for general relativity experiments. There is also an Italian project called the Galileo for Science project, which aims to perform a set of measurements in the field of fundamental physics by exploiting these two satellites. The goals of the project are numerous. providing a new measurement of gravitational redshift, measuring the relativistic precessions of DORESA and MILENA orbits, placing constraints on dark matter in our galaxy, providing a relativistic positioning system, developing new models for non-gravitational forces, and finally developing a new accelerometer concept for a next generation of Galileo satellites. These activities are connected to one another, and the IAPS is involved in all of them except the fourth. Let's start from gravitational redshift, which is the relative frequency shift of an electromagnetic wave due to the gravitational field of a body. General relativity gives this expression for gravitational redshift, but as we know, it is not a test of the theory, since it can be derived by imposing the validity of special relativity and equivalence principle. However, gravitational redshift plays a key role since it represents a local position invariance test, according to which the result of any local non-gravitational experiment is independent of the space-time position in which the experiment is performed. To this purpose, an alpha parameter is introduced, and it is not zero in the case we have a violation of the local position invariance. In 2018, the French colleagues of Sirte and the German colleagues of ZARM measured the alpha parameter by improving the result of gravity probe experiment. A deep analysis was conducted on systematic effects related to Earth's magnetic field, temperature variation, orbits, and clock solution. Our goal is to provide an estimate of alpha with an uncertainty of less than 2 multiplied 10 to the minus 5. Another goal of the project is measuring the relativistic precessions of the orbits. General relativity predicts that for a non-rotating central mass, there is a precession effect on the orbit of a satellite connected with this central mass, and this is the Schwarzschild or Einstein precession. If the central mass rotates, the lens steering precession occurs. There is also another effect that we have to take into account, which is the geodetic precession or de Sitter precession, due to the motion of the Earth-Moon system in the gravitational field of the Sun. And these precessions have already been measured by using the largest satellites. Now, the challenge is exploiting the Galileo satellites for these measurements. From the table, we can see the precession of the argument of pericenter and of the node for the Galileo satellites and for the largest satellite. As we can see, the orders of magnitude are different. For the Galileo satellites, the values are very small. So for us, measuring these effects, in particular the lens steering and the geodetic precession, will be a challenge. Regarding constraint of dark matter, we know that topological defects could arise from ultralight quantum fields that would create dark matter. The hypothetical passage of dark matter as a topological defect through the orbits of the Galileo satellites constellation would cause possible transients in the energy levels of the onboard atomic clocks. And analyzing 16 years of GPS data, Robert and his team found no evidence of domain walls, which are a dark matter candidate. But this study can be in principle improved by using the higher sensitivity of the atomic clocks of the Galileo constellation. Finally, another goal of our project is to develop a new concept of accelerometer that can be used both as a platform instrument and as a scientific instrument. We aim to overcome the current limits of the INAF IAPS accelerometer, such as the one for the Baby Colombo mission, in order to measure the onboard non-gravitational accelerations down to a precision of 10 to the minus 10 meters over second square. The mathematical and physical context on which the Galileo for Science project is set up is the one of general relativity. General relativity leads to Einstein's field equations, according to which mass energy tells geometry how to curve and geometry tells mass energy how to move. The Einstein's field equations can be written in a very simple way if we consider the weak field limit approximation. This linear approximation can be applied in the case of the Earth, since we deal with a source whose gravitational field is weak and whose rotation is not relativistic. In this context, the metric tensor of the spacetime G mu nu can be treated as the sum of Minkowski spacetime metric tensor and a small perturbation. Defining in this way the perturbation and imposing the gauge condition, we obtain the Einstein's linearized field equations. And this is the solution far from the source. Phi is the Newtonian or gravitoelectric potential, and A is the gravitomagnetic vector potential in terms of the angular momentum J of the system. So we have a gravitoelectric field produced by masses analogous to the electric field produced by charges, and we have a gravitomagnetic field produced by mass currents analogous to the magnetic field produced by electric currents. Here we reported the analogy of classical electrodynamics equation and the classical geometrodynamics. A coil traveled by a current density JE, to which we can associate a magnetic momentum, generates at distance r a vector potential and a magnetic field. Similarly, a coil traveled by mass current density Jm, to which we can associate an angular momentum, generates at distance r a gravitomagnetic potential and a gravitomagnetic field. Moreover, general relativity predicts that the spinning mass will drag inertial frames along with it, and this is the so-called frame dragging or lens steering effect. So, as a consequence, in general relativity, local inertial frames are not only determined by the distribution of matter, but they are influenced by the distribution and flow of mass currents and mass energy in the universe. Therefore, the gravitomagnetic field associated with this phenomena would produce a force which is similar to the Lorentz force, and this is the gravitomagnetic force. To pursue these numerous goals of the project, a fundamental point in our analysis is obtaining a satellite orbit solution precise as far as possible. And so we intend to perform an accurate, precise orbit determination, which is the procedure through which we can obtain the satellite orbit with high accuracy by fitting the tracking data with the set of dynamical models that take into account for different effects, including the non-gravitational perturbations. Non-gravitational perturbations are the most difficult to model because of the complex shape of Galileo satellites and their attitude law. In this context, we want to take a step forward compared to the state of the art in the reliability of the dynamical model used for the determination of the orbits of these satellites. So, an enhancement of the non-gravitational perturbations models is required, in particular the one for the direct solar radiation pressure, which is the major perturbation. To derive the perturbative acceleration, our ultimate goal is to develop a finite element model of the satellite. And to do this, an accurate and detailed knowledge of the geometry and the physical properties of the various satellite constituents is required. Moreover, accounting for umbra, penumbra effects and multiple reflections is fundamental. And in this context, to do this, So to take into account mutual shadowing effects, we plan to apply the so-called ray tracing technique. As a starting point, a 3D CAD of the satellite has been developed, as well as a box-wing model of the satellite, which simplifies the satellite structure into a central bus and 2 rectangular solar panels. The surfaces have been characterized until now with the geometrical and optical properties provided by Galileo metadata by ESA. In this slide, we show the effects of our box-wing model on the orbit of a Galileo satellite on circular orbit. With the box-wing model, we calculated the accelerations, and through Gauss equations, we derived the rates of the eccentricity and of the node. Then we compare our box-wing model predicted error with the orbital residuals obtained with the software Geodyne. As we can see from the plot, there is the evidence of the direct solar radiation pressure in the residuals, and this is a very positive and encouraging result. Although our precise orbit determination are preliminary, there is a good agreement between our preliminary precise orbit determination performed with the software Geodyne and by using satellite laser ranging data with the ESA POD. Regarding gravitational redshift measurements, we started the analysis of the great clock data. The theoretical clock bias can be calculated from the precise orbit determination, and general relativity gives this expression. But to perform a reliable measurement of the gravitational redshift, a corrected clock bias has to be calculated from the clock bias solution and by taking into account a relativistic a priori corrections, which was already included. So this corrected clock bias will be compared with the general relativity prediction in order to estimate the alpha parameter. Our goal is to provide an alpha estimate with an uncertainty of less than 2 multiplied 10 to the minus 5. So an accurate and reliable measurement of the gravitomagnetic field of the Earth is not only an important test for the predictions of GR in the weak field, but with this measurement, we can investigate at least 3 main issues. Intrinsic gravitomagnetism, which describes the curvature effects of the related to mass currents, and not simply the effects related to the motion of a body in a static background field. Strong fields and compact objects that we will see in the next slides, and Mach principle. The sentence, inertia here arises from mass energy there, summarizes very well the meaning of gravitomagnetism. So we can interpret the lens steering effect or the frame dragging effect as a weak general relativity formulation of Mach principle. Gravitomagnetism can explain the mechanisms at the basis. Gravitomagnetism, together with the magnetohydrodynamic phenomena, can explain the mechanisms at the basis of the accretion of matter around rotating compact objects, and also the mechanisms of the accelerated charged particles with the simultaneous emissions of powerful radio jets. These effects are related to the gravitomagnetic field of the rotating compact object, and the models which describe the physical classical interaction of the flow of matter with the rotating compact object produce relativistic effects. So that produce the drag of the accretion disk and the spinning and the alignment of the radio jets with the spinning of the rotating compact object. In this context, numerical relativity plays a key role, but to our knowledge, there is not yet an observational direct evidence of the role of gravitomagnetism in this strong field regime. Regarding compact objects, gravitomagnetism measurement can be useful also to constrain the internal structure of the neutron star. This binary system of neutron stars can be useful not only for studying possible alternative theories of gravity, but also for their gravitomagnetism measurements. In this context, the gravitomagnetic precession of the orbital plane due to the angular momentum of the system plays a key role. From the observation of this phenomenon, we are able to have a direct measurement of the angular momentum of the system, and from this we can derive the moment of inertia of the neutron star. Then, as we can measure independently the masses of the two components of the binary system, from the moment of inertia and from the masses, we can obtain the radius of the neutron star. And so we have the mass-radius relationship, and in this way, we can constrain the internal structure of the neutron star. Measurement of gravitomagnetism can be employed also to constrain the presence of dark matter in our galaxy. Here, we reported some proposals in this field of research to which our group participates. For example, the Lagrange dark halo detector, whose main scientific goal is to look for gravitomagnetic effects related to the angular motion, to the angular momentum of the Milky Way, both in its dark and visible component. Indeed, if the Milky Way is immersed in a dark halo, it is reasonable to detect such gravitomagnetic effects related to the motion of this huge halo. And in this proposal, the experimental setup consists in placing spacecraft on the Lagrangian points of the Earth-Sun system. And each station emits electromagnetic signals along close paths between the Earth and the Lagrangian points. The essence of the experiment would be the measurement of the flight times along the closed paths made at one station. In this context, a gravitomagnetic measurement has already been achieved by Crosta and the group of INAF Torino and University of Torino by exploiting the precise measurement of Gaia of the peripheral stars' velocities. They developed a relativistic model in which the weak gravitational contribution of the off-diagonal terms of the metric, so the gravitomagnetic terms of the metric, could explain the flatness of the Milky Way rotation curves. There is also another way to constrain the presence of dark matter by assuming a different nature of dark matter, not a particle-like nature, but as we know, a possible dark matter candidates are also the ultralight quantum fields that would create macroscopic objects or clumps. And an example of clumpy dark matter candidates are topological defects, such as domain walls. And the global navigation satellite system can be useful to search for such objects because we can interpret the satellite constellation as a big detector of dark matter of a size of thousands of kilometers. And as the Earth moves through the dark halo, the interactions of topological defects, such as domain walls, with the atomic clocks of the constellation would cause a sequence of perturbations in the atomic clocks that propagate through the constellation. And assuming a quadratic scalar interaction between dark matter and clock atoms, we are able to express the relative frequency shift as a function of the relative variations in the effective values of fundamental constants. So, in conclusion, we presented the main goals of the Galileo Core Science project and their theoretical framework. We showed our preliminary results regarding box-wing model and the precise orbit determination, and these results are good and positive. By acquiring more detailed information about the geometrical and physical characteristics of the satellite, we will be able to build an improved box-wing model and finally a finite element model of the satellite. To this model, we plan to apply the so-called ray tracing technique to further improve the estimates of the non-gravitational perturbations models. Then we showed the fundamental role of gravitomagnetism in the field of relativistic astrophysics, such as in binary system of neutron stars for placing constraints on their internal structure, and also in the active galactic nuclei physics for the explanations of accretion of matter mechanisms and the radio jets emissions. Then in cosmology, because gravitomagnetism measurements will allow us to constrain the possible presence of dark matter in our galaxy, and also in the alternative theories of gravitation, since we can compare the general relativity predictions with other theories of gravitation. So thanks for your attention.
Thank you very much, Feliciana, for being perfectly in time, actually, for the great talk. And, you know, a lot of food of thought, I would say, a lot of material, and as I said, fundamental physics is really fascinating. Again, as before, I invite everyone to make questions or raising at the end or writing on the chat. In the meantime, I have myself, so this is a field that really is not my field of research, but it's really fascinating. And I was wondering, at the beginning, you mentioned that specifically for the dark matter, that is a technicality. So you say the current Galileo configurations, you used this terminology. It will be used now. I was trying to look at the slide again, because I was wondering when you said, it was at the very beginning, during the description of the project, particularly the dark matter. Exactly, the current constellation of Galileo Fox satellites can allow an improvement of this. So what I was wondering is, when you say current, you mean the present day or the...
No, sorry. Now I'm more precise. In this case, we can talk about in general of the GNSS, so the Global Navigation Satellite System, in general, and also the Galileo constellations. So it's not the current, but we can do this experiment with the GNSS constellations, and in particular with the Galileo constellation Fox satellites, because they have the onboard atomic clocks are very performant. So the work of Roberts et al. In 2017 exploited the GPS constellation. So in general, this kind of experiment can be done with every constellation of satellites, but in this case, we want to take a step forward to improve these constraints on dark matter by using the higher accuracy of the Galileo satellites.
Yeah. So
the clocks of the Galileo satellites.
Okay, I see. Thanks. I see that Dietrich has raised a hand. So Dietrich, please go ahead with your question.
Yeah, thank you. Very interesting talk. My question concerns the binary pulsar.
Yes.
And you mentioned that one might be able to see a change in the inclination of the rotation axis of a pulsar. is this an absolute measurement, or is it measurement of the difference between the inclination angle of the disk and the inclination angle of the rotation axis?
No, it is, so the gravitomagnetic field can be explained, the alignment of the powerful radio jets, the emission of the powerful radio jets with the spin of the rotating central object. So it is the alignment between the jets with the rotation axis of the rotating objects. So
I mean, the way it is written on the slide, this is a differential measurement of the difference between the two angles. How could one distinguish between this effect and the effect of a third body in the system?
Sorry, where in slides? I don't understand what you refer.
If the binary contains a third body, that body may change the inclination angle of the orbital plane.
I think yes. I'm not an expert on this field, but because this is a binary system of neutral stars. If there is another object, it is a more complicated problem. Because in the binary system, we can make this measurement because we can measure in an independent way the masses. Because it is a binary system, if we have another body, it is much more complicated.
Okay, thank you.
Great, Feliciana, thank you very much. We are running to the end of the event. There are no questions on YouTube. So at this point, I would like to thank the speaker again. Thank you, Feliciana. Thank you very much, Carolina, for the talks. Thank you very much, people who attended the series, the talk today and the series during this month. We today, as I said, we are closing the series of events, and we wish to our speakers today and also to all the speakers of the series good luck and congratulations first of all, and good luck and all the best for your career, for the coming months, and for the PhD defense.
Thanks a lot.
It's gonna be great. Good luck, and hopefully we will see each other in person now, and let's see what the future reserves us. But for now, let's close the session. And again, thank you very much. As I said, you can go online and check the material. You can see the videos. And I would like to remind everyone that at ESO we have a dedicated program for early career scientists. Is a visitor program that is dedicated to you, and you can apply and you can come to ESO and spend up to 4 months to a visit to our premises, both in Santiago and in Garching. And this is there for you to use. You can find information on our web pages. Again, the program is called Early Career Scientist Visitor Program. Please have a look at it and spread the voice to your friends and colleagues. And we are looking forward to welcome you at ESO as soon as possible. And with that, again, thank you very much. Thank you to the attendees. Thank you. And and see you next time. See you soon.
Goodbye.
Bye bye. Ciao.
Ciao, grazie.
Thank you. Bye bye.